Because if there are jurors that like
Has anybody got anything specific that they're looking at? That because there's plenty of strange things in there. I
The
was going through, and they spend an awful lot of time on the conditional probability, which is good. And then they spend a lot of time on these tables, like contingency tables, in the third part. And we'll look at some of those today in the 120. But I just want to see if you got anything specific.
I do have two problems. It's asking whether or not the events A and B are mutually exclusive, independent, both or neither. And I didn't know that they could be both or neither. So, uh,
Yeah, it's not the easiest thing to understand. I'll
right.
show you what I got here.
Okay.
I amended my notes with some things to give us some extra stuff on this. But here's the things that are important that we can figure it out with. All right. If two sets are independent, all right, if they're independent, then this right here is your friend. If they are independent, then the intersection, or another way of looking at it is A and B is equal to the probability of A times the probability of B. And the reason that is because when it's dependent, remember that the first event, probability A, affects the second one. And so that's why that holds. Because this right here, it looks kind of menacing, but all that simply means is that we're adjusting that probability to show that event A has occurred. Event A affects event B. All right. So this one right here is the important one here as far as independence is concerned. The other thing is here, mutually exclusivity, or to be mutually exclusive, then the probability of the or the union is equal to just the probability of A plus the probability of B. If they have any overlap, which is what this one states, then they're not mutually exclusive, of course. And these are written the same way, I guess. Actually, there's two more things here that can also be helpful. This is the same thing that was up here, the second green check. But these right here can be helpful for determining independence. All right. If we have independent events, then the second probability, in other words, the probability of B given A is just probability of B. In other words, this changes to this with independence. Likewise, if you have them backwards, the probability of A given B, then the probability of A given B would be equal to the probability of A for independent events. So let's see if we can get to a question that you got. Since I did them, I don't know how to get them back in there. This is the problem. Like if it's a review, you can take it again.
So it's I go back to there's
Can
like
you
view activity.
screenshot it? What is
Activity.
it?
If you go on the Newton homework, you can go to activity details and you can
Okay.
put whatever question you want that you got wrong or
All right. Okay. So okay. So where did you say you go?
so say go to
Just
probability
go back
part
and
one or part
just
two.
go into the same one again.
Yeah.
Okay. I know I've done it, but I can't remember if it. I'll let you just go through them. I guess you can just.
And then
Oh, you know
scroll.
what? Technically, I did this one, but I did it in the student view. I didn't do it in. I did it in the actually in Allen. I mean in Newton.
Oh,
So
so
this
there's
one will
probably no
let me
activity.
go in. So this one will let me go through all of them. So let's just go and see. This looks like it might be interesting. Yeah, this is deals with mutual exclusive. All right, you have a fair die with 6 sides containing the numbers 1, 2, 3, 4, 5, 6. Just a plain old die. So we got two events, A and B. A is rolling a 1 or a 2. All right. And then B is rolling an odd number. Now, what I want to do is put here the odd numbers. Oop, just 6 die. Now, do these two sets have anything in common? One is both a 1 and it's odd. So they're not mutually exclusive. So there we go. That's probably the best way to do it because it's not the last one. I'm not sure what they mean in the common outcome of a one. Oh, yeah. That's right. I thought they were talking about one is in the sum of probability. Okay. So that's the answer on that one. Does that make sense?
Yeah.
When you got both independence and mutual exclusivity, that's when it gets tough. And you got to think about it. All right. So event A is rolling an odd number on a fair die. So if you write them out, it might be a little bit easier to see. Even number. There we go. All right. So A and B are mutually exclusive. A and C are mutually exclusive. But B and C are not mutually exclusive. So A and B are mutually exclusive, right? Because they don't have any common ones. B and C are mutually exclusive, as we said. They're not. They've got 4 in common. So A and C are also mutually exclusive because odd and even, they interlock. They don't overlap. They complements. All right, let's see. So there are evenly weighted game spinner has 5 numbers on it, labeled and counted in a color piece of spinner. Oh, I was also going to say, in that notes, I put this little thing here. It may help you understand if you want to open that up and look at it. It's not really anything to teach. I could go over it, but it just shows the concept of mutual exclusivity and independence to help you understand them better.
I find the
It's
videos in Newton are really helpful. Um,
yeah,
like
that
it's
yeah.
kind of
I
dumbed it
watched one
down
this
for
morning.
me. Yeah.
Yeah, she's a pretty good teacher. I actually worked with her for a while. She's a nice lady. She doesn't teach here. I don't know where she's in Indiana or something. All right, where am I at? Oh, here we are. All right. So we got a spinner with 5 numbers on it. It doesn't really matter what it is. It's a game of chance. So it's going to be the same whether it's a die or a spinner or what. It's just the number of outcomes is going to be different. So there are 3 colored red, 1, 2, and 3. And then B, I'm sorry, the blue is 4 and 5. So B and R. Okay, consider the Venn diagram below. Each of the dots outside the circles represent. Oh, this one's a pain in the neck. But watch me. All right. So what you got here is you can go on even or you can go on blue. And this is kind of what makes it a little bit, because they talk about event A. Oh, okay. So event A is even in that. There we are, greater than 3. So now let's look at what they're telling us. Somewhere they're going to tell us. 3 are colored red. All right. So 1, 2, and 3 are red. Two is going to go right here, right? So I got to keep scrolling up. But the 2 is the only one that's even. All
But
right?
they share the 4, right?
They share the 3, don't they?
I thought it was greater
And
than 3.
let me see if I can
4,
make it
5, and 6,
smaller.
right? I don't know, 4 and 5.
So 4 and 5 are going to be over here because it's greater than 3, right?
But it's even
No,
as
that's
well.
even. Yeah.
Yeah.
And then that one goes there, greater than 5. Yeah, it's even. All right. So the other ones, red 1 and 3, would go in here as well, right? Nope,
Uh,
nope, they're not. That's right. They're not red. So they're going to have to be over here. But they're not greater than 3.
1, 2, and 3 go in red, right? And they share 2 and 4,
But they're
maybe?
not even. Isn't that what that is? Even? So they can't go over here and they can't go over.
Oh, I see what
Let's say
you're saying.
be greater than 3. This one's annoying. I went through and tried to do one of these yesterday. Actually, it's before a class, and then we didn't talk about it, so I kind of forgot what it was about. All right, so 3 are colored red, and 4 are blue. So this is right. 1 and 3. But see, the 4's got to go over. I don't know. Let's look at something.
Blue is just greater than 3, so the R1 and R3 go in E. I don't know.
Yeah, this is a crazy thing, and I apologize for it being a pain in the neck. I was so busy this morning working on that third one that I forgot all about this stuff. And these are just kind of weird. So 3 are colored red. So I guess the other ones have got to be outside. I mean, that's the only
You may
thing.
not use all the dots.
So those are odd. So they can't be in even and they can't be in blue greater than 3.
Yeah.
So this should be it. Let's double check. So red 2 is even. So it's on its in that one by itself. R4 is greater than 3 and it's blue. 5 is greater than 3 and it's not even.
I think
And
that's right.
then 1 and 3 got to go outside because they're not even and they're not blue. Does that look good?
Yeah, and I even
All
forget
right. Okay.
that.
Because I remember doing this yesterday and I got so frustrated with it and I just forgot about it. Because it's taking you back to the Venn diagram stuff. And that is helpful to do that. But all right. Now, this is the rule that we talked about yesterday, the addition rule. It harkens back to chapter 2, where we see it strictly in terms of the number of elements in a set, or the number of elements in the union of two sets. We would just replace the P with N, but it's the same thing. We're just going to now write the probability. So if they're mutually exclusive, then of course the intersection is going to be 0 because there's no overlap. All right. So they just given us an example. Event A, 1, 2, 4, and 5. Event B, 5, 6, 8, 9, 10, and 12. And then in this one, 3, 4, 7, 10, and 11. And so they calculate the probability of A. There's 1, 2, 3, 4 over the total of 12. So the probability of A is 3. So it's basic. This is the basic probability we were looking at. We're just looking at it with a Venn diagram. So probability of B, 1, 2, 3, 4, 5, 6 over the total of 12, or 1/2. And the probability of C, 1, 2, 3, 4 5 over 12. And then once we got those, we can use that formula. So if we want to find the probability of all of them, of A or B, in other words, these two circles, the green and the blue, forget about the red, then we're going to put the probability of A plus the probability of B minus the probability of A and B, which is just 1. So that's 1 out of 12. So what you need to do, just in case you're not following that, they should have left them. And this is the thing that I'd like to stress. When you're dealing with the addition rule with or, don't simplify like they did there. You simplify at the end. So what I'm going to do here is I'm just going to go back. So there's that one. And this one would be the 6/12. That's the B. In case you're wondering, this is the probability of A. And this is the probability of B. Minus the probability of A and B. I'm going to put intersection B to keep it short.
Yeah, and I had to like freshen up on multiplying fractions, dividing fractions,
Yeah, and that's why I tried to offer that advice about
keeping the
for the or, don't simplify them
yeah.
because you're going to have to add them. And if you have to add them, you're going to have a common denominator. And the way they were originally, they already had the common denominator. So now it ends up being 10 minus 1 is 9 over 12. And then you simplify. Both 9 and 12 are divisible by 3. So 3 goes into 9 3 times and into 12 4 times. So there we go. That's how we use that rule. And we don't necessarily have to have a Venn diagram. We could have these things here. The Venn diagram just makes it easier to see. All right. So they did it again here. A and B are mutually exclusive now. So see that? There's no minus is missing because the intersection of A and B would be 0. And I just like to add that because it's the same formula. It's just when they're mutually exclusive, there's no overlap. It's the same formula. All right. I'm going to see if we can go ahead and get to a problem that somebody might have had an issue with. I know you directed us here, and you can't really move around. You got to go in order that they give them. All right. A 2014 Pew analysis found that in the U.S., 29% of households fell into the low income tier, and 51% of households fell into the middle income tier. If the income tiers are mutually exclusive events, low income 0.29 and middle income 0.29. What is the middle income? Well, that's really pretty simple because it's just going to be adding them up, right? It says that they're mutually exclusive. Should be right. So 0.29 plus All right. It doesn't say what they wanted in, do they? Sometimes they want percent, but that's what they wanted. All right. So is an additional rule for mutually exclusive events. Well, this is the same thing. It's just 0.22. So 0.68. So all we're doing is just adding those up because they're mutually exclusive. So all we got to do is add them up. There's no intersection, no overlap. So independent events, that means that one does not affect the other. So when you handle independent events, it's simply the and of both, or the intersection of A and B is equal to the probability of A times the probability of B. And we're going to get into that a little bit later. I didn't really touch on the and very much, but that's important. All right. Let's see what they say about this one. Because sometimes if you don't read what they show in their examples, you won't pick up on little nuances. A game requires that players draw a blue card and a red card to determine the number of spaces they can move on a turn. Let A represent a red card, 1 through 4, and let B represent a blue card, 1 through 3. What is the probability that a player will draw a red 2 and a blue 3? All right. So there's 1, 2, 3, 4, 5, 6, 7. Cards. So there's only one red 2. All right. So 1/4. And that's basically like saying drawing a 2 given it's red. In other words, the condition is it's red. Same thing for this. So we want blue and we want a 3, and there's only one of those. So now these are independent events. At first, I was a little bit confused because there's 7 of them. So I was kind of thinking, well, there's one red 2 out of 7. But these are separate, the blue and the red. All right. So since they're independent, we just, we want and, then we just multiply them. Very similar to that one that I did yesterday, where you flip a coin and then roll a die. 1/2 times 1/6, which also gave you 1/12. All right, let's see what we can do with the independence. That's the one that I'm a little bit worried about. Now, also too, they bring up this formula, which is the conditional probability formula. As I had said, is I'm going to go with that today, but they get to it a little bit earlier than I generally have in the past. So I'm going to get to that today, but we'll talk about it now too. So this is algebra stuff, and you don't need to know the algebra stuff as long as you know that formula. So here's the and probability. The probability of A and B is equal to probability of A times probability of B. Now, if we want to solve for this one right here, we're essentially what we're doing is we're dividing both sides by probability of B, just to show you why it happens. Because we want to isolate the probability of A. So these two are one now, they're gone. All oops, you know what? I messed up. I put B instead of A. So this is what we call the conditional formula. So the reason why because this right here just becomes 1/1, and all you got left is just probability of B. This right here is what we call the conditional probability. So if we have a scenario like this, they tell us that the probability of A and B happening is 0.54. The and is always up at the top. Okay, see that? So that 0.54 goes right there on top. That's the and. And then the probability of A goes down there, and that's 0.9. Now, you got to be mighty careful about this because it's easy to do. You're always going to have that larger number on the bottom. All right. The larger number's got to be on the bottom because if you turn that around and put 0.9 over 0.54, you're going to end up with an invalid probability because it would be greater than 1. So that formula is going to be very helpful. They have a lot of things in here that use that. So 0.6. All right, let's see what else we can do. All right, first year nursing students are randomly assigned to classes in a nursing school. Let A be the event that they are assigned to an anatomy course, and B be the event that they're assigned to a psychology course. So probability of A or anatomy. Are any of y'all studying to be nurses?
No.
Okay, I just was curious. If you have to have another math, generally the one that the nursing people like you
We
to do,
take
I think
those
all the
classes
allied.
though. Yeah,
What's that?
I'm in surgical tech and we take those classes.
Yeah, and if you go in like nurse and what's the other one? Radiology. They want you to take statistics, which is 203, and this is a good springboard into statistics. All right. So if A and B are independent events, then it's simply going to be oops, so 2/3 times 2/5. Sloppy, but 4/15. So 2/3 times 2/5. So 2 times 2 is 4. 3 times 5 is 15. No common factor. So that should be it. All right, good. First, let's read the assignment's learning objective. Get familiar with this topic by reviewing instruction and answer a couple of questions. Well, I'm not sure what they mean. Okay, if you roll a, I guess this is the questions they're talking about. If you roll a fair die and then roll a second fair die, what is the probability that you roll a 1, 2, or 3 on the first and roll a 5 on the second? All right. All right, so there's 3 over 6. Which is 1/2. And when you're doing the multiplication, it really helps to simplify them first. I'll show you what I mean. Because if you do 3/6, and then this one right here is just 1/6. All right, so the probability. So we're just going to multiply them. So that's going to be 1/2 times 1 over 6. So the independent events, so nothing strange on the second one. So this is 1/12. And they want it as a fraction. Okay. So if an officer pulls someone over for speeding, the police can give either a ticket or a warning, but they can't give both. Okay. If the probability that, in other words, so that's your clue right there that it's mutually exclusive. If the probability that a police officer will give a warning for a speeding is 0.03, and the probability that a police officer will give a warning, give a ticket or a warning is 0.52. Now, let me kind of try to show this within the context of the formulas. So it's ticket or warning is equal to 0.53. Actually, it's 5.2. So there's a 2 there. It's a little bit better. There we go. All right. All right. Now, the probability of warning All right, so what we got to do is we did this last week when we were reviewing. I think there was where we're using that formula, and then we got to use. They're going to ask for the missing piece. So again, this is what the formula is. So they're mutually exclusive. They tell us right up there, and they tell us that can't give a warning for and a ticket at the same time. All right, so on this one here, we know this part. And we know this one. All right, so the one that we don't know is this one. Let's just call it X. Well, now we're just going to get the X by itself. So we get rid of this part. And if we do it on this side, in order to keep our equation balanced, we have to do it on the other side. Same sign. All right. So these will be gone. And this will simply be x is equal to 0.49. Right? Something seems strange, but that's right. So, and if you like the whole explanation, they do it probably a little bit better than I do, because they start out with that, and then they solve it for by just taking the A, the B over, and leaving the A over. And then it's kind of more or less the same thing. I just did it slightly different. But they solved it for A by subtracting the B from both sides, and it goes away on this side, but over here it just attaches to the A or B. So now you just subtract the 0.03 from the 0.52. But with these, there's always more than one way to handle it, because you can go, when you got an equation, you can go either side when you simplify it. For mutually exclusive, okay, so this is adding. An electric company has to track on-time payments and late payments for each customer each month. So it is impossible for a customer to pay on time and late each month. So again, mutually exclusive. If the probability that a customer pays on time each month is 0.55, and the probability that the customer pays late or on time each month is 0.82. What is the probability that the customer pays late each month? All right, so we're going to have to do the same kind of thing. We don't have to use the formula, but we just need to set it up with these values in place. So I'm going to go ahead and write it out. So it's time or late is equal to the probability of time on time plus the probability of late. Okay, and this one here is 0.82. And then we know on time is 0.55. And then that's just going to be plus, and we'll just say that that's an X right now, just to keep it simple. So now the goal with algebra is to isolate the variable that you want to find. So when you don't know it, you want to put everything else on one side and you're trying to find on the other side, because that's called solving for that variable. In this case, it's going to be nice and neat because these values are both numbers. Sometimes, if in algebra, you still got variables and you have to subtract, and it gets really confusing. But we don't have any of that here. And then so we're going to subtract it from this side too. Always same side, because we want to get rid of this. This was the idea. And to get rid of it on the right, we also do the exact same thing, the negative 0.55 on the left. So then this is 0.27 is equal to the probability of late. So this is 7. All right, got through one objective. It's almost halfway though. That's good. All right. So this is just about mutually exclusive events. A college offers its students multiple study abroad opportunities for the semester. Given events A and B are the two items or events mutually exclusive. So probability A is the probability of studying in Asia, and B is the probability of studying in Europe. And they're mutually exclusive. Okay, so yes, the mutually exclusive. I'm thinking they're not, but let's just look. Yes, the events are mutually exclusive because probability of A is not equal to probability B. All right, let's look at that thing. So mutually exclusive events, their intersection is 0. That's the main thing that we're looking at. And that they also just add with no intersection because that's 0. All right, what happened to it? That really doesn't have anything to do with mutual exclusivity. It's one of those two things.
Outcomes in common, right?
So yes, the events are mutually exclusive. They have no outcomes in common. Well, that's the opposite of that's the wrong definition anyway. Mutually exclusive is they have no. Huh, this one has kind of got me a little bit stumped. What do you think, folks?
Okay, I think they're mutually exclusive because it equals 0, A and B, like it's 0. A intersection B equals 0. That's mutually exclusive, so they have no outcomes in common, right?
Okay, yeah, you're right. It's that simple. I was looking for a formula, and so I was tempted to look at this one, but that's not right.
Yeah.
I wish they'd have said that the probability of A intersection B is 0, but you're right. All right, 2 to. All right. So if events are mutually exclusive, that means they don't affect one another. We also know 2 other things. In other words, they just multiply to get the probability of and. And also that the probability of A given B is equal to A, and the probability of B given A is B. All right. If they're independent, find probability of B. So again, if they're independent, So probability of A and B is equal to just the probability of a multiplying. Okay. So on this one, we know and we know A. All right. Now this is different. This is multiplication here, so we can't just subtract that 0.6. Let's just go ahead and put a X right there so it doesn't look so intimidating. So that's 0.6X. So the property we were using for the or when we had to add is called the addition property. So in other words, you can simplify an equation by adding the same thing to both sides, to eliminate things. Well, here, there's no adding here. So this has got to be that we divide by both sides. So I'll show you what I'm talking about. As a matter of fact, I'm going to write it slightly different. All right. You can kind of think of it sort of like this. 3x is equal to 9. Then what do? You divide both sides by 3. So then x is equal to 3. So the same thing here, we're just going to divide both sides by that 0.6. And dividing the 0.6 by itself means that that's now just x, or in our case, probability of B. And then this is 0.5. Don't believe me? Watch. It's 0.3 divided by 0.6. So now they want it as percent, so we got to multiply. All right, so if I multiply times 100, that gives me the percent. And then this gives us a little bit of review on stuff. Oh, they did it a little bit different, but it was the same thing, actually. I didn't think about it like that, but that's all we were doing. Is, just using that conditional rule to get it, because they're just the same equation in just different forms.
So usually whenever you're dealing with the mutually exclusive ones, you're doing addition, right? The addition rule. And then
Yeah, exactly. Because
it's multiplication.
yeah, and with independence, you generally deal with multiplication.
Okay.
Yeah, that's correct. All right, so end of end. So use the multiplication rule. If you roll a fair die, 6-sided, then flip a coin, what is the probability that you roll a greater than 1 and get a heads? All right. So let's just write those down. How many numbers are greater than 1 on that die? There's 5 of them, right? Out of 6 total. And then the other thing is probability of ahead. And that's just the same old 1/2 thing. And since they're independent events, it's just as easy as multiplying them. And then multiply for fractions, numerator times numerator, denominator times denominator. Oftentimes, if there's any factors that are common, in other words, if there was a factor between 5 and 2 and 6 and 1, which there isn't in this case, if you take it out there, you won't have it won't be so hard to simplify. In this case, we don't need to simplify it, but because that's already simplified. There's nothing common between 5 and 12. All right. Bring on that confetti. All right. Now, these contingency tables, essentially what it is, it's a contingency table is specifically one where you got 2 rows and 2 columns. So this was just a generic one. So the choices for the rows are have a certain characteristic, do not have a characteristic, and then the columns are follow a rule, do not follow a rule. And then there's going to be numbers in all of those, okay? They do have us complete some of them, but usually they've got, some numbers missing. Let's see what they want us to do on this one. So what you got to do is they want us to fill the missing parts. And that's the video. If you like that, you can go ahead and do it. But essentially, all of these total up across. So on this one, 5 and 10. No, we don't want that one. Let's do this first one. So this one's got 3, but it doesn't matter. It's still a contingency table, but there's a specific kind. All right, so these all have to add up to 21. So what I'm going to do, I'm 27. So what I'm going to do is I'm going to take the 2 numbers I have, 11 plus 7. So I'm going to subtract those from 27. So that means then what goes here is 9. So that's replacing that. All right, so now I'm going to go over here on this side because I'm only missing 1. So 27 from 50. So this is going to be 23. So see, these should total up on these tables. These should total up going across. So now if we have 5 and 10, we've got 15. And I'm going to subtract from 23. Then that means then 8 will go here. No more B. We filled him in. Total up going down here. So 11 and 10 is 21. 9 and 5 is 14. Now, it's a good idea to double check these because that was one of the things that I had trouble when I did some of these, especially that one where you had to fill in the whole one. you got to make sure that they total up. So 9, 11, and 7 should be 27. Good. 5, 10, and 8 should be 23. Good. And then on the bottom, 14 plus 21 plus 14. Oh, I forgot. I had 14 and not 15. So 50 is right. 27 and 23 is 50. 7 and 8 is 15. 11, 10. So they're all good. So that's what we're doing when they're asking you and they're showing you all this. That's all the subtracting and adding that I did. All right, let's see if we can do one of these. All right. Now, for conditional probability, okay, you're given as the denominator. Let me try to explain, because that's the condition. In this case, the condition is the person does not support the environmental bill. All right. So I'm going to go to that one. And I'm going to go over to the total. See that? There's the do not support. And it's a total of 33. Probability of transit given not environmental. Okay. So again, whatever is in this position is your denominator, because this means right is given. Probability of taking public transportation given they do not support environmental bill. So that means down here is the 33. All right. Now, what we got to do is remember our formula that we're using. Where's it at? Like this one right here. The and is on the top. So that means both. So I got to find that intersection. So over here, do not support, but take public transportation. So there we go. That's it. When you got these contingency tables, it makes it easy. You look for the given to determine your denominator, and then your numerator is the intersection of both. Intersection of public transit and do not support. No common factor. That was one of the good things that I noticed about most of these is that there weren't a whole lot of fractions to simplify. So hopefully that's a bit of a blessing, because I don't like doing them either. All right. All right. So 60 high school teachers in a certain school district were asked about their highest level of education. The incomplete contingency table below shows the number of English, mathematics, and science teachers that have a bachelor's or master's degree. So let's try to finish it out. All right. I'm just going to start here on this row. That row should add up to 25. So we've already got 20, 16, I'm sorry, 14 and 6 is 20, right? So that means there would be 5 right there. 5 plus 14 plus 6 give us the 25. So that's good. 5 and 10, 15. So they should total up both ways. All right, let's see. I'm going to do this one next because it's only missing one. Go the easy route. Because if you try to do these, it'll be a little bit harder. We could also do this one, but I'm going to do this one. So what I got to do is I'm missing a number that gives me 60. So I've got 20 and 15 already. 20 plus 15 is 35. And then I'm going to subtract that from 60. So that means then the number that's missing here is 25. 15 and 25 is 40, plus 20 is 60. Then we can do one of these two. It doesn't matter what. 14 plus what is 25? I think it's 11. I'll double check it. 14 plus 11, 25. Same thing here. 6 from 20 gives us 14. Let's double check all of them. So 5 plus 14 plus 6 is 25. 10 plus 11 plus 14 is equal to 35. Good. 10, it's not 10, it's 15 plus 25 plus 20. I'd already done that one, but do it again. And then going down, 5 and 10 is 15. 14 plus 11, 25. 6 plus 14 is 20. So this one's good. All right, given the completed teacher table above, find the probability a teacher has a bachelor's degree, given that they are an English teacher. So that means then we got to have the English teacher. So this is the probability of BA given English. So what goes on the bottom is the English people. How many English people are there? 15. See that? That's the total of English teachers. Now what I need is find the intersection between English and bachelor's degree. So this is 1/3. And they kind of show you the same thing they did with 2 different colors. You're looking at the total English teachers. Look at the total first. That's your denominator. And your your numerator is the intersection between English teachers and bachelor's degree, which is 5. All right. That's probably a good place to stop. Let's see what this next one. Same kind of thing, I think. Let R be the event that a randomly chosen person has red hair, and green be the random person has green eyes. Place the correct event in each response box. Given that the person has red hair, given goes after the line. And then this would be your green. All right. Given is the denominator. And it's the one that comes after the line. Given. All right. So that's probably enough for right now. Anybody got any questions? I'll see you in a few if you don't. We probably still will do a little bit of this. I do want to finish up that the and chapter. I'll try to do it kind of quick, and then we can come on some more of these because I don't believe you got to the ones that we originally asked about, which was independence. I know those are in here. All right. Well, I'll see you in a few minutes. Okay.
Thank you.
Mm-hmm.
Okay, thank you.
Okay. Bye bye.